Hello. Okay, so Mr. Brandon, pleasure to have you with us. All right, thank you so much. Thank you.
Hello?
Hello.
Hello? Yeah, I'm good.
Hello. Oh, that works. Hi, everyone. So we have a panel today. I'm moderating. I've never moderated a panel before. Let's see how I do.
Really, I'm surprised. I'm on stage with a couple of times already, so.
Yeah, I've been on panels. So so we're going to talk about zkVMs, and we're going to talk about a cool part of them, their design and architecture and performance and these kinds of things. I'm super excited to get into it. So yeah, I mean, I guess before we jump in, people should introduce themselves. Should we just go down the line? Go ahead.
Yeah, sure. Yeah. So my name is Ming. I'm the chief scientist of zkVM. Proudly to be your host here. Yeah, that's me.
I'm Brett Carter, VP of Product at Risc. I'm the least qualified person technically to be sitting up here, but it's an honor. Yeah, definitely have some thoughts about zkVM design and excited to chat with you all.
Hi, I'm Hadas. I'm a researcher at Lita, a zkVM company.
Hi everyone, I'm Bobbin. I'm a project lead at Polygon Miden and the designer of the Miden VM.
Great, and I guess I should introduce myself. I'm Brandon. I'm the CEO of O1 Labs. We're also working on a zkVM as one of our projects, but I'm not going to talk about that today. I'm here for you. So, shall we?
Please.
So yeah, when designing a zkVM, how do you think about, or how is this different from a traditional virtual machine? Anyone want to take it?
Yeah. Yeah, so there used to be a saying that you do a proof once and then you can run everywhere. But here, doing zkVM, you're actually not running everywhere, right? It's just a proof. You don't really run it. So I think that's the major difference between design a virtual machine and the zk virtual machine. It's for proving, verifying. It's actually not for executing. So yeah, so that's something to bear in mind. But we'll delve into that, I'm sure.
Yeah, I guess from Risc perspective, I think the team made even before I joined, made a really big bet on really optimizing for accessibility. So that was the idea around selecting Risc-V as the ISA that we were targeting, is to really try to make this available to average developers. And so in that way, I think our focus was similar to designing a regular VM. We really wanted developers to be able to use tooling that they knew. Obviously, Rust wasn't quite as popular within the blockchain and crypto space as it is right now, but yeah, that was really like a key consideration for us.
Yeah, I think it's just about what operations you're optimizing for. So traditional VMs, you're really you're optimizing for what happens on the CPU, and then in a zkVM, you do have to optimize for that, but first you have to optimize for algebraic operations. So for example, at Lita, one of the reasons we've seen such speed gains compared to competitors is because we create our own compiler as well as so we have the prover side and the compiler side, and the design things go together. So by building our own ISA, we're able to actually optimize for the algebraic operations.
Yeah, I mean, I agree with all of the comments, but I think like there are multiple dimensions on which you choose, right? You can choose like where are you on the developer friendliness, so to say, and then there are different gradations. So like you can build as Risc is doing, for example, the kind of common ISA. You can do as Lita is doing, like different ISA in different compiler, or you can even come up with a different language, for example, that is like there are different gradations in that design choices. You also want to choose like what set of features you need to support, and this is use case driven, right? So for example, do you need very small proofs, or like how small your proofs need to be? Because if, for example, if you're doing something to be able to do client-side proofs, this is important. You need to send them over the network, and then the difference between like a few dozen kilobytes versus 50 kilobytes versus like a megabyte is a huge difference. So you want to pick that. And then as you've said, it's basically also how arithmetization friendly you can try to make it, and like how do you want to handle recursion, for example? Do you optimize it to be very recursively efficient or not, or it doesn't matter that much? So like, there's a ton of design choices that the usual VMs you don't care about necessarily as much, but here it's like probably half a dozen of dimensions on which you need to make a choice, opinionated decision, and then, you know, it depends on the use case.
May I add, since everyone's spoken, may I add that I said earlier that it's actually not running everywhere. It's a proof. So I think the elephant in the room is that why we chose different ISA to prove, right? So
And which is better?
yeah, it's a little bit contentious, this topic, but let me give my take.
Go ahead.
So actually, Owen and I think we're in the camp of MIPS, right?
I'm the moderator.
Okay, all right. But yeah, but they're with the same with us. And I believe you guys are Risc 5? Risc 5, yeah. Both of you are Risc 5, right?
Custom.
They have their custom.
Oh, okay,
customized.
yeah. So I think this is not like related to ZK, because we kind of use this kind of same kind of approach, like a Plonky, and Plonky 2, some Plonky 3, and then a Graph 16 for verifier. So I think that the choices between a little bit, not just engineering, but also like market penetration consideration, right? Adoption. The elephant in the room is that, for example, like StarkNet, they have their own custom like VM, like Cairo. I once heard one of the engineer saying that, for example, proving like Sharp 206, they're 933 times faster than RISC-0. So they can do that because they have a really simple virtual machine, right? But that virtual doesn't exist anywhere else, so you have to just completely like, kind of just immerse in their everything, their ecosystem. But I think for a lot of use cases, we like to verify real-world programs and verify them on-chain for a broad range of application. So I think that's the reason why some of us chose this hard real-world RSA, for example, MIPS and RISC-V, right? And for us, we want to kind of, and then Lita is there because Lita can kind of optimize their own VM, which is very kind of similar to Risc, right? But very optimized for ZK. And I think in the future maybe that's your world. I have to yield to you guys. But the consideration is that you kind of keep kind of balance that you balance for real world kind of market penetration. For example, MIPS is around for like decades. Very simple. It's simple relatively, right, compared to these customer ones. But for the real world CPU, MIPS is really simple, and then also kind of considering that it should be also good for ZK doing ZKP. So I think that's every project kind of catering to their own market segment and try to be as best fitting for their use cases and audience. So I think for first of the zkVM design, I think this is I think this is the case for choosing ISA, and then we have other considerations vectors as well.
So
I think so. There are approaches, right? So like ISA, then you like what developers care about. The developers want to write in a language that they know. They don't necessarily care what's running underneath, but like there are obviously trade-offs. So like we discussed some approaches where you have the common ISA that you have compiler tools that already compile to that. You have like Lita and kind of Miden approach where you try to compile, like let's say from Rust and custom ISA. There are other approaches as well which are not represented on this panel. For example, you can interpret programs, so you can like have something like is not even compiled, and there are pluses and minuses to this as well. Like developers just cares that they can write in a language that they understand. They don't even care if there is like a compiler underneath or whatever. So like I would say, but all of these choices come with other trade-offs, right? Like Risc-V, you get tool chain already existing. You don't need to invent or build a compiler. While like in Miden and Lita approach, you do need to have like some compiler, modifications. Or maybe, I don't know, Lita, to what extent you do it.
As well, yeah. You can probably just pick a program compiled 20 years ago and still generate.
Yeah. And an interpreted approach, you don't even need to worry about compilation. So like differences between compiling in different ways, you like saying, okay, like it's a program, you commit to the code that a high-level code and it interprets it. So there are pluses and minuses everywhere.
So what are the, I guess, with the custom ISA approach, as you're mentioning, you have to build your own, some parts of the stack, right? Why did you go with that choice for both of you, Lita and Miden, versus a more traditional ISA?
So what we found is that by designing our own ISA, we're able to really reduce the number of algebraic operations we have to do in the end. And so, on the ZK side, as I think you said, we are all kind of doing the same thing. And I mean, you can always use the most you can do is use the state of the art in zero-knowledge proof research. But to have an edge on top of that, you have to reduce something somewhere. And I guess the easiest thing for us to reduce is the number of operations that we have to do, which can happen.
You have like 2 registered, right?
Yeah.
We have many, many
yeah,
more.
exactly.
Yeah.
We don't have as much. We have like special purpose registers and things like that.
Yeah, I would say basically like efficiency is one consideration because like, for example, for Miden, we need to be able to run it in like 2 gigabytes of RAM and generate proofs in 2 gigabytes of RAM. So you can prove it in a browser on a phone. You can have a lot of like setup times. I think in a lot of existing ISAs, you need to spend some time to set up. Like there are some number of cycles spent on just setting up the program and initializing everything. In Miden, your program could be as small as like 256 cycles, for example, and that's enough. I mean, you can do a lot in 256 cycles, but if you have a small, like that's like the minimum instead of like a few tens of thousands of cycles that sometimes it takes to like just initialize things. So the efficiency is one. The other consideration is like if you need features that some ISAs don't provide. So Miden is like, as a project, we care a lot about privacy specifically. So we need to build a kind of an environment where you have private and public programs interacting with each other seamlessly. So you need to build in, let's say, context isolation at the level of the VM, where like if you are running in one context and make a call in another context, they can't access memory from the other context. It's not a kind of something that you build on top of the VM. It's a core property of the VM itself. And then you can take it even further. Like we are not there, like with Miden, but for example, you can implement a full like kind of resource-based model where there are resources that can be shared, and the sharing of resources enforced not by the language, by the VM itself. And that gives you, especially in a blockchain context, that would give you a lot of cool properties, but no existing ISA supports that.
Right. Yeah, from the Risc side, what
I think actually this is maybe, I don't know if anybody's ever explained this well or how many people know this, but we actually do have a custom ISA specifically for our recursion circuit. So like we have the RISC-V circuit, it proves RISC-V cycles. It's got a couple other widgets on there. There's like a big int multiplication component. There's a SHA-2 accelerator built into the RISC-V chip. But we took and I think the question also has to do with like sort of timing, like when did you sort of start these systems? I know, like Bobbin and their team were so early, sort of like forging ahead, doing really cool stuff, building specifically for a blockchain. And when we looked at RISC-V, people were kind of like, that's a dumb idea, proof systems are too slow, and so we've been mostly focusing on optimizing the prover, and we've had a lot of success there we'll maybe get into. But what's interesting is I think we were the first team to take this approach where there's actually 2 circuits in the protocol. The second one is a dedicated recursion circuit, and this merges segment proofs, like individual RISC-V sets of RISC-V instruction proofs, through a merge tree like into a succinct proof. And that recursion circuit actually has its own ISA for efficiently and quickly verifying these proofs. And there's a couple predicates in there. So like you have to like take one of our segment proofs and do a lift, sort of lift it into a dialect in which we can then sort of join proofs into a proof set. And so there's kind of actually a mix in our protocol.
So Brett, is the recursion circuit, that's its own VM with instructions? It's not a custom?
Yeah, it is.
Really? Cool.
Yep, absolutely. And
why is that? Instead of just being like a domain-specific circuit that does the one thing of...
Yeah, that's a good question. So we've also built all of our own compiler technology. And you mentioned earlier we're all using Plonky 2 or Plonky 3. We actually have our own Stark-based proof system, so it's not true for RISC-0. which Plonky 3 is great, and there's a lot of similarities to what we're doing. But at the time, it didn't exist, and so we built our own proof system. And so we describe circuits in one of two ways, either in our DSL called Zurgeon. We've built like a whole stack. It's DSL, compiler, proof system, VM, etc. And I'd have to ask Jeremy because he's the one who figured this out, but it's just from an automation perspective, it's way easier for us. Once the RISC-V circuit updates to just sort of update a constant, all the compiler takes care of all the rest. So it's really a convenience and maintainability decision.
Yeah, so we've started to touch on performance. With each of your specific zkVM approaches, how do you keep performance in mind? Like what tricks have you done? Like what are the design considerations that you've made to make performance better or make it easier to optimize?
I think like I said earlier, like the industry is kind of just similar. We all read the same papers, and kind of engineering teams have figured out kind of similar paths to solutions. So I think that it just came down to like each like engineering trade-offs that you do yourself. How much you use the lookups, the table, because we're kind of dealing a much complicated like a real CPU here. We have many more like registers, and also we support the 4 GB of memory. So all that needs to be taken into consideration of our proofs, and of course there are also specific example for hash and something you have to do optimization maybe separately, and there are definitely rooms for improvement to squeeze. So I think we're because we're kind of like latecomer, but I think it's worth it that we're catching up, and also we're benefited from that. MIPS is a very stable and simpler instruction set. So and it's also very stable. Like a couple decades, there's no bugs. And because it's simple, there's no like floating point, everything. I think it was like we're at the beta 3. It's kind of on par, and maybe in some cases, even kind of near the top. So we're satisfied. We're still improving, but we're satisfied.
When you consider all the steps necessary to sort of write a program, generate a proof, verify it on chain, there's so many things you can optimize. It's actually quite a complex process. And I guess one of the things that RISC-0 did early on is, it was obvious, Ellie, from Starkware wrote the Stark paper. Jeremy, our co-founder, read it, and he was like, "This is amazing. I think this, zero knowledge proofs will be practical, but people aren't going to write circuits." And so when he started looking at, we talked a little bit earlier about ISAs, but he also realized, we need better and faster proof systems in order to make this feasible. And so, at the time, Cairo and Starkware, I think they were using like a 256-bit field. The Polygon team innovated the Goldilocks field, so that brought fields down to 64 bits, and like proof systems were getting incredibly fast. I remember seeing a tweet that like I was working at O1 Labs with Brandon, and Polygon, like in Plonky 2, somebody was doing like hundreds of hashes in a second, and I was like, what the hell? This is incredible, And Jeremy's one of the key innovations under RISC-0 was like his discovery of the Baby Bear field, which is a 31-bit prime field that actually works really well, surprisingly well, with proving RISC-V cycles. And so again, just sort of reducing the size of the field. Now, we're going to clearly, in Binius, we'll eventually go to a 2-bit field, but that was a really key consideration in making things go fast, if you will. One of the underrepresented things, though, is like we tend to think of benchmarks and performance as single machine performance. And in reality, zkVMs, and particularly the approach that many of the general purpose ones are taking today, actually enable dramatic improvements in performance through parallelization if you're optimizing for wall time. So if you're just trying to make a proof go fast, we can generate an Ethereum block, a proof of an Ethereum block today. And like Bobbin mentioned earlier, we're actually interpreting the EVM bytecode. So this isn't a dedicated zk EVM circuit, but we're actually running an interpreter in RISC-V, and we can generate a proof in 60 to 90 seconds right now for the average Ethereum mainnet block. And so there's just like sort of all along the way, then how do you, many of us do this, we convert the Stark to Snark, lots of opportunities for performance improvements there. And so there's really, in terms of like just pure speed, go burr performance, there's just so many different opportunities to optimize.
Yeah, I agree with that. I mean, there's no one way. But what we do, I think what's nice about the way our and probably most zkVMs are designed is that it's very, very modular. So for example, we, like when we're developing, we end up optimizing on a chip-by-chip basis. And then after you write something, then doing benchmarks and making sure that everything is getting faster. And then, yeah, on the proof size, side, there's a lot of new optimizations coming out. Field size is one of them, or picking the correct field for the correct application. I don't know. We're going to be moving to sum check-based snarks soon because those you can totally avoid polynomial quotients with that, which is a bottleneck. So I think it's just about, but what's interesting, I think, is that you can get really excited about one thing speeding up and then find out that it affects the system only a little bit. So I think one key lesson with optimizing things is always take a systems level high view approach to it. Otherwise, you'll end up being disappointed a lot.
What do you mean by choosing the field? Is that a parameter in the?
Yeah, I guess there are some field agnostic snarks so that they work over any field. And so, for example, if you wanted to verify signature schemes in a snark, you can use the same field that the signature scheme is using, so you can avoid non-native operations, which can be a large constant overhead. Yeah, because you have to do modular operations in the circuit.
But I think one of the advantages of zkVMs in general is that you can be field agnostic. You can swap out the proving system agnostic even. You can swap out the proving system and instruction set hopefully remains the same, and therefore you don't break everything else in kind of what was written against it. So that's, I think, is a major kind of power of just going the VM approach, especially the VM approach that doesn't use field-specific operations or doesn't assume something about the proving system and things like that. That is very cool. I think, yeah.
I was just gonna say, yeah, you could consider that an aspect of performance, right? What does your maintainability look like? How maintainable are the systems that you're building? And I think we tend to just think how fast can you prove something, but there's these other components that sometimes are often much, much more expensive, for example, how do you find talent to maintain a system, write zero-knowledge circuits? We've seen, because of general purpose zkVMs and really what the Miden team had really kicked off this innovation of VMs, is much more maintainable systems that are much less costly to build and yeah, maintain.
Yeah. I would say Starkware was the first production-ready VM. Miden was the second one.
Miden was the second.
Yes, but overall, so in terms of optimizations, basically it's picking again for your use case. As an example for Miden, we need to pick we're trying to make it fast for our specific roll-up use case, right? So we're making some things faster that maybe in other systems you don't care about, but in Miden we care about. For example, we need to make our goal is you should be able to prove a simple transaction on the phone in under 2 seconds. And so we may not be able to do it with ECDSA signature, for example, but we can pick a post-quantum signature that's standardized, like Falcon, for example, and have specific circuitry as a chip in the VM that allows you to prove Falcon signatures very, very quickly. And that's what you optimize for. I think the other aspect of this is as you said, as you solve for one bottleneck, you come up with a different bottleneck. So you always jump from one thing to another as you progress through this optimization. I think what will happen kind of going forward, your witness generation will become much bigger bottleneck than anything else, especially as we move toward hardware, because everything else is very easily parallelizable. And your proof generation part is actually going to be a small part compared to the witness generation part.
What do you mean by witness generation part?
Computing the trace.
It's already a bottleneck in our proof system in many cases. It runs at 30 to 50 megahertz, so we can commit to 30 million to 50 million RISC-V instructions per second on a pretty decent machine. But because everything else is parallelizable, and if you have a really big block that's say 2 billion cycles, it's already the bottleneck in many cases. So absolutely agree.
You mean interpolating the polynomial from the data?
Yeah, so the way that execution works in our zkVM is first we generate an execution trace and make, generate witnesses between the segments, the individual segments. So there's some commitments that take place between these segments. And so as we're just running the program itself and doing this witness generation or making these commitments, that can only run, it's single-threaded, non-parallelizable, and it can only run at about 50 megahertz today.
Oh,
yeah.
Interesting.
And if this this is becomes your ceiling of what you can achieve, because I think again, especially with hardware generation, 90% of the time is going to be witness generation time, and hardware will take care of, all parallelization will take care of the actual proof generation time.
Why isn't it parallelizable? Because you have to go through the execution trace?
It's a single-threaded program that you are usually executing.
So this is interesting, right? Does anyone foresee a future where we're going to change, like adapt to the way we write our programs to be able, so that the execution trace can be computed in parallel. So I guess like in a traditional system, you know, some kind of concurrency model. Is that something
you can
anyone's
already
thought
do that
about
today?
yet?
So like if you're using a general purpose zkVM and you want to prove Ethereum blocks, there's like a number of ways to do that, right? You can prove an individual block, you can prove sets of blocks. You know, I know, Uma and their team, right? Like in OP Sysync, there's a nice graphic in one of their blog posts where it's like they do these range proofs of like say blocks 1 to 10 and then 10 to 20 and then merge them after that. And so you can kind of parallelize the execution
But
by,
those are separate ZK
by splitting up
yeah.
the proofs,
But
exactly.
like one program definition in Rust,
Yeah.
but you can compute the execution trace in parallel.
That'll be interesting.
Has anyone thought about that?
No.
Yeah,
I guess
I
it's
don't
too far away.
know. We're
Yeah,
thinking
cool.
of things to make execution way faster. We have some ideas, and like where we can get to like 10 to 50x probably faster than we're executing now. But I don't know that you can actually you sort of in order to generate a proof, you sort of have to constrain yourself down to this program that does run linearly. And so I don't know how that would happen other than splitting the proof itself.
And there you can maybe, I don't know, your CPU runs at 5 gigahertz, right? Like maybe you can optimize things so like your single-threaded execution will run at like a tenth of that. Like maybe, there is room for improvements and like optimizations. Well, you'll get to like 500 megahertz, but that will be your ceiling in terms of what you can do, except for like maybe long time in the future where you can actually have a custom like Risc-V chip with an extension that, for example, generates the trace as it executes, and that would be like cool, but it's also like far away in the future.
What's funny is we're already talking about performance getting close to like regular CPU performance. There was a team we were talking to, I won't name their name, but they're like, oh yeah, we need to get to like 50 gigahertz of proving performance. We're like, there's no regular processor that goes that fast, So these are good problems to have. Like the space is advancing so quickly that actually like 50 megahertz, if we get to 500, and 10x improvement from here, we're starting to talk about real good, reasonable performance.
Yeah, I remember Jody mentioned that with this massive parallelism, that 12 seconds for a certain block, something like that.
I'm sorry, what was that?
12 seconds for
Just doing the
block.
execution on a block?
Well, yeah.
Proving as well.
proving,
So
yeah.
like if you can actually prove Ethereum block in 12 seconds.
Oh, real-time proving. Yeah.
Real time.
Yeah.
But I think you still have the delta, right? Because like they actually can execute the block in like 1/10 of that time, or like sub-second for sure. But proving but I think we'll get to the point where you can execute and prove basically at the same time. You need hardware for that, and you need
Yeah. I think like mainnet, for example, the average, and this is like Shanghai blocks, like there's all these caveats here, but roughly you need in Risc-V cycles 170 megahertz of performance to keep up with the chain. And so if our executor is only running at 50, you can do other things like move them out of Risc-V cycles, do dedicated accelerator circuits or precompiles. There's definitely some things that you can do, but yeah, I think 170 megahertz is roughly where we need to get.
Yeah.
for
So
that.
why don't we go into this like domain of accelerator circuits or custom chips, or what do each of you like? How do each of you think about this? Yeah, precompiles, accelerator circuits, custom chips. Like, what is the lingo that you use? Why do you use that? Is there even something standardized across the industry? Like, how do these components fit into your stacks?
I don't think there's a standard anyway. Like there are also like these ZK acceleration chips out there. So yeah, it would be nice to have a standard or something, but I think everyone is just to make their own. Do you guys work with any
Brandon,
yeah,
do you mean standard terminology or
not hardware? Yeah, like within your zkVM, your precompiled circuits or custom accelerator, like virtual chips. I heard some.
Yeah. I mean, we call them chiplets. People usually call them chips or coprocessors or state machines. I think there's like across different projects, people use different terminology. I think there are also different ways to do them, right? So there is probably, I know, like about half a dozen different approaches of how you do them. Like Miden does them in one way, Cairo does them in other ways. Like I think Risc0 does them in different ways. I think Sysync does them in different ways. So like, and I think Lita also. So there's like different ways of how you can have chips or chiplets, how you tie them together, because there's different permutation arguments you can do. You can do it through recursion, for example. So I don't think there's a standard. People are experimenting, and again, like some things apply better to some use cases. Some.
So what experiments have you done? Like what experiments has the industry done? What I guess like why are for those of you that are using these accelerators, like why are you doing the approach that you are?
It's funny because I think we have 3 or 4 different approaches that we've tried or are doing in our proof system. So it's not even like just a one or the other opportunity. So I mentioned actually that we have inside of our Risc-V circuit is sort of 2 helper functionalities for SHA-2 acceleration and for big int multiplication. And that's actually like one approach, which is to actually just write it into the Risc-V circuit itself. We can do the same in our recursion circuit. So RSA, for example, actually fits quite well into our recursion circuit. We have an accelerator precompiled for that. That's coming out in the next couple weeks, and that is actually the same approach, but in our recursion circuit specifically. And then there's something like Ketchek, for example, where we're writing what we would call like a machine accelerator, or like a dedicated separate circuit where we include a recursion predicate. Like we generate the separate proof, but then use recursion to sort of stitch it into the Risc-V execution. So that's 3 different approaches that we're taking just in our proof system alone. But I think it's still like to be determined if there's one exact way to do it. It's also algorithm specific, right? So like I don't know this exactly why, but RSA just like fits quite well in our recursion circuit, and so we're sort of taking a case by case approach.
Yeah, I think everyone's doing something like that. Just we don't call it like a chip in chip, but but do you need like a special instruction to your virtual machine? Did you need compilers to support all that?
Do we need a compiler to support all that?
Yeah.
Yes, absolutely.
Yeah.
We've definitely doubled down, like, I don't know, 10x down on compilers. We spend a lot of time maintaining our compiler, writing this DSL. What's really nice is like you can get, for example, there's like work in progress on actually making SIRCOM R1CS compatible with our compiler.
Right.
So you can actually compile any existing SIRCOM circuit down to RISC-0 Stark circuit. So yeah, this is all compiler dependent for sure.
Right. For us, like we're looking both the back and the future. So because, for example, like a Rust, I think a lot of new applications, especially like blockchain applications, are written in Rust. So yeah, so we're trying to do like these experiments to accelerate and optimize them in the Rust compiler support for our zkVM. And we're also looking back for compatibility because there are a lot of legacy apps for these special, like for example, edge computing devices, like sensors. They're very standard, and so we hope that one day that we can just take one of them and have them proved on chain. Those are the ones that needs blockchain and crypto support. For consumer devices, yeah, maybe not that much. So, so MIPS is very good in that, stable, simple for decades. And yeah, and for the future in the Rust and everything. So it's a balanced approach. But I think it's fascinating that you guys are innovating in the look in the future to Risc-V definitely has a lot of the modular support for that. Yeah.
I think it's not good to have too many custom chips. So it's one thing you have to think about when you're doing it. It's like, does it actually address a general problem? So like, it makes sense to have one for a hash, because you're always going to be using hashes, or for recursion, because that is like reduces proof size for general circuits. So I think before we introduce custom chips, we always think about, is it attacking a general problem actually?
Yeah, what's interesting, we mentioned that you tweak performance somewhere and it creates these like follow-on or secondary or tertiary side effects. One of them of like chips is, okay, now you have like basically different proofs to optimize. So imagine you have hardware that's built to accelerate Risc-V proving. There's ways to design it so it could be more flexible than this, but now all of a sudden that doesn't, you have a new proof that you're running that hardware does not accelerate. And so, to some extent, there are definitely trade-offs that you take.
Yeah, so Miden approach is kind of like, I think, similar to what Lita is doing in some ways, but also like similar to RISC-0 in some ways. Basically, we have a handful of chips, or chiplets as we call them, that do hashing, that do like binary operations, and a few other things that we care about specifically for recursive proofs. And the approach to handle other computations that you want to accelerate is through recursion, where you kind of like do a syscall in a, and like this syscall like expects that there will be a recursive proof, let's say, for ECDSA signature or for like something that we do not accelerate, and then those, if you have your inside the VM, the recursion if well optimized, then verifying those recursive proofs would be cheap. And I should mention that this is still in development. We don't have this fully working in production yet, but this is the approach to kind of like have a handful of chiplets, because they also increase like the other consideration for Miden is that we want proofs to be small. And therefore, like we have very small number of columns. So like we have, I think 70 columns overall right now. And adding a chip could result in more and more columns depending on how you do them. And so we want to limit that, and we actually like stack chips on top of each other so they share the trace, and this way you kind of reduce the proof size. But yeah, so like handful of chips, and then everything else handled through recursive verification of specialized circuits.
And you mentioned you can use like some equivalent of syscalls to kind of access this logic. Is that, I guess, how does everyone think about this? Because especially for the standard architectures, like MIPS or Risc-V doesn't know about verifying a recursive proof or executing a Ketchak coprocessor or something. So how do you escape the like sort of native instruction set?
Right. Actually, for MIPS, it's quite simple because it's the oldest one out there. So the syscalls for the CPU. So we don't have many, maybe less than 10. So it's quite straightforward. Yeah, this is the in-CPU one, not the system level one.
Yeah, I mean, I guess this is punching a little above my weight, technically. But we use syscalls to essentially sort of escape the Risc-V execution and say, I'm going to call into this other circuit and a recursion circuit in order to use what we call like a machine circuit, sort of like a dedicated separate circuit that we'll do recursion for. We have to write a recursion predicate for that particular circuit that gets added, incorporated into our recursion circuit. And so, yeah, that's essentially how we enable these two, disparate circuits to communicate our systems.
Cool. Should we? I think we have like less than 10 minutes. If there's any question in the audience, we can take one, or I can ask more.
I got to say something real quick.
Oh, go ahead.
It's funny because in a lot of this stuff, we don't talk about security. I think that's
Okay.
something we have
Let's
to
talk
talk
about that.
way
Go ahead.
more about. We're building zkVMs not to just like generate proofs in space, right? Like we're building like financial systems and decentralized systems on top of these. And so, yeah, no, I don't necessarily have anything to pontificate about, but we do as a space, I think, need to start emphasizing the security of these systems.
It's time to pontificate. You
Yeah.
brought it up. So how do you think about security in Risc 0? And then we can go around the room. Like what aspects of the design of the zkVM or the design or the mechanism by which you're developing the system do you like? How do you think about security in those processes?
Yeah. Number one, like audits are a bare requisite. It's a bare minimum, not a bare maximum. Like I think we tend to think like, oh yeah, it's audited, therefore it's good to go. It's like, no, it's actually, just like bare minimum. And so I think one of them is, how many bits of security are provided by the underlying proof systems or the way that these circuits are constructed. And I know that's something that Paul on our team just has spent, copious amounts of time making sure that we have peer-reviewed materials on the bits of security provided by our proof system. Another one, and this is true of our proof system, and I think some of the other Stark-based VMs as well, but like for example, when you select what we call a segment and what the SP1 team calls a shard, when you select the size of those shards, like in our system, you configure a PO2, which is like how many, to the power of 2, how many Risc-V instructions do you want in a segment? That actually does determine the security parameters of the system. So by default in our proof system, it's set to 20. So there's about 1 million to the 20 or 1 million instructions in a single segment. If you go up to 21, that brings the bits of security provided from roughly 99 targeted bits of security. By the way, this is conjectured security. You can also get to proven security in Stark systems, but this brings the security down from 99 to 98 bits, and we think that's like the appropriate lower threshold. You could actually like hard code bigger segments into the zkVM, but security would go down essentially a bit at a time. And I don't think this is like a component. Many people don't understand this, and we've in our docs there's like 6 dedicated pages on security, because this really matters. There's like so many ways to potentially exploit these systems. You have the proof system, the circuits themselves, multiple proof systems, right? Because we do CIRCOM, and we're all doing wrapping the Starks and Snarks, etc.
I mean, on that note, I think I guess what I was going to say is that there's many aspects of security. There's the security and the soundness of the proof system itself. There's making sure you write the code as is specified by the protocol. And then once it's deployed, there's actual just like end-to-end security the way there is in any software system, and there's so many ways that could go wrong.
Then the
and probably
contracts to
formal
verify them, right? It
verification,
just
you know,
keeps going. It just keeps
but it is
going.
something to focus on. But in terms of conjectured security, I'm a PhD student as well as working at Lita, so I focus on this a lot. And I think conjectured security is an interesting thing, like especially with the Fry-based proofs. To get the proof size to be like tolerably small, you end up having some kind of not so great provable security that you like compensate for with proof of work. And I think that's probably fine, maybe, but I think it would be nice. I mean, I think it's probably wise to focus more, like as a research community, we should focus more on getting the provable security down and without compromising proof size, because yeah, I think it's not good to use conjectured security.
Can you explain more, like what is this term conjectured security? Like what is the specific, you know?
What is a conjecture?
Yeah. What is a conjecture?
Yeah. Yeah.
Well, that's not a question for me.
Well, yeah, I guess there's a few conjectures flying around. So, okay, one of them is that you can, okay, well, let's see. Provable security is saying something like we have a proof, a mathematical proof, that there is a probability of like 2 to the negative 100 that a prover can cheat. Okay, that's great, because that's a really low probability, and it's proven. Now, let's say we only have like 2 to the negative 80, so that's less good, and now we'll do 20 bits of proof of work. And what that means is that the prover is has to, it's like normal proof of work. Like the prover has to create a certain number of hashes before it's allowed to prove. And so the idea is that, 2 to the negative 100 security is good because it means that a prover would have to try so many times before they get somewhere, more times than what they have computational resources for. So it's like, okay, if we just throw that at it, then it's fine. But I don't know.
And conjecture, that means in this case is that we don't have the mathematical proof,
Yeah.
but nobody knows how to exploit it yet. It doesn't mean that there is somebody may find a way to exploit it, but we just don't know of a way to exploit it right now.
Which is the same security we get from SHA-2 and other hashes.
Right.
Like this is actually, we're often operating in conjectured security. And somebody else would have to describe why this is true, but in Starks you have this unique characteristic where you can actually prove the security of the system, like she was describing a minute ago. Is like, you sort of know how much work needs to be done, and therefore you can actually generate a mathematical proof of the security.
It's true that hashes are conjectured, however, they have had decades and decades of like scrutiny from communities, from the entire security community, not just like the cryptography, not just the zero knowledge proof community. But
And
like,
where does this like 2 to the 20, let's say, bits of proof of work come from? Like, is it just natural in the fact that the work that you're doing to do these zkVM proofs for like a moderately sized program is computationally intensive, or do you actually have to, in your implementation, have loops that their only purpose is to do this proof of work?
yeah, that's pretty much
It's
what
a
it is.
parameter that you say, okay, for this proof I want to have 20 bits of work. For this proof I can go to 24. 20 bits is usually fairly acceptable. It's negligible. It's very, like on a CPU, it's very quick. You won't notice it from the user. But you can go like up to like, let's say if you wanted to get more bits of security, you could go like 24, 28. It just like, it will take much longer to generate the proof, but you can compress the proof size and make it smaller because you maybe, or either you compress the proof size or increase the security level. So there is all these trade-offs. I think the other aspect of this is that like we're all now using, or most of us are using like around 100 bits of conjectured security. Like there are very few projects that I'm aware of that like use more than 100 bits or use provable security. I think provable security is definitely one thing we want to go to. The other aspect is we probably want to go to more than 100 bits of security, and this is not something that we need to do right now, my personal opinion, but like in a span of like 5 years or so, ideally we would get to 128, because like, Bitcoin network, for example, does like 96 bits of work in a year.
Oh.
So
Yeah, that's true. Also, computers are getting more powerful, so you have to be able to adjust for that.
so hopefully like 5
yeah.
years from now, we will all be in like 128 bits of provable security. For this, we need to make advances both on like implementations and like theory and all of that stuff. I think one other thing I want to say, so this is there are different facets to security. Like this is one. I think the soundness of the the constraints is in my mind is one of the biggest ones, where
That's true.
in other places, like I think we have tools and figuring out how to do it. Soundness, I think like you can do formal verification and other things, but like I don't think anything is bulletproof in there. And like you try to make constraints as simple as possible. You try to like audit them. You try to do it, but like I think this is like a big thing that worries me personally, is like a basically missing constraint problem.
Yeah, I don't think, like a really important conclusion of what we said here is, I don't think people realize you can trade off performance for, like security for performance.
Yeah.
You know, one way to make it go faster is just to actually make it less secure.
But
So-
then what's the point of doing it at all?
Yeah, exactly. So
that
we need to
makes-
be much more conscious of the fact that security really matters here in performance context.
Are you hit?
No, yeah, I'm just saying that we need to get more people to generate all that usage, right? Otherwise, if nobody's using it, then why worry about security, right?
Which converging on a standard would help for that as well. Yeah.
And
Right, yeah.
Brett, are you saying that other projects aren't setting their security parameters properly?
Brandon's trying to make this spicy, but I'm not going to let him.
Okay,
Yeah, I mean,
I'm
look,
just
like,
asking.
You should have a verifiable trusted setup. Like, I'm not going to point fingers or name names or anything, but like, yeah, I think we've gotten, because these proof systems have been so slow historically, we've become laser focused on performance, and we're not talking nearly as much or thinking nearly as much or asking nearly as much about the security of these systems.
Yeah,
Okay.
that's true.
I also want to make one distinction, sorry. Like frequently, or at least in the past, and maybe still right now, like you can have like much lower level of security that people run, even like there was some like at 60 bits or 40 bits, and this is obviously unacceptable in a kind of open setting, but like sometimes those systems are like, I think it's okay to run, let's say, at 80 bits if you're centralized prover, you are the only one doing proofs. Like as soon as you go decentralized and like people can do proofs, like that's like it becomes super important. I mean, you don't want to have like 20 bits of security or 40 bits of security, don't get me wrong, but if like 100 bits or 80 bits may be acceptable for now if you're like a centralized prover because you don't, nobody else can generate proofs. You're kind of like making sure that you are the ones who cannot cheat. You're kind of only protecting against yourself, and you are in that case a company that people can come after and all of that stuff. So it really depends also in what setting you're running. So in some cases, like it may be okay-ish, at least for now. In some cases, you should like obviously do much better.
That's true.
Thanks. So we're out of time. Thank you, everyone.
Yeah, thank you.
I mean,
Thanks, Brandon.
Oh, we have a question. Oh, we're allowed to do a question.
Okay,
Great.
thank you. Really fast question for Risc 0. So you mentioned that you just need like 20 seconds to prove a block for the Ethereum. So I can assume that the block gas would be reach up to 30 million gas, right?
I'm sorry, I don't understand the question.
Okay.
The 30 million gas fits in where? The proof itself is only less than 300,000 gas to verify on chain.
Okay, so my question is, how much dollar do we need to prove a block?
How much dollars? Is that
Yeah.
what you said?
Yeah.
What kind of computer do you have? No. Yeah, so we shared some numbers. Tycho did a significant round of testing on like sort of our private cloud cluster, a service we called Bonsai. And we got up to, I think, 25 megahertz, so that was 90 seconds to prove the average Ethereum block. I don't know how much, obviously Ethereum targets 15 million gas. I don't know that that's the actual average, but so that block in 90 seconds is about, let's assume, about 15 million gas. We've since, like in our next release, it's probably 40% plus speed improvement on that, just because, again, the executor was the bottleneck there, and we're up to about 35 to 40 megahertz on this instance type that we use. And so that'll bring the time down to about 60 seconds. Cost on that is well under $1 to generate that proof. I don't know the exact numbers right now, but I would say if you have you're running your own hardware, including the cost of that hardware, cost of financing that hardware, and the power, everything, it's like close to 50 cents, which is really incredible. We can prove mainnet Ethereum today for about a little over $40,000 a month. And again, it's getting like next release, that'll get 40% better. We have at least another 4x in mind. There's just tons of optimization still. So it's just, it's getting ridiculously cheap.
Awesome.
Thanks. We are out of time, right? Okay. Well, we're out of time. Bye.
Thank you, everyone.